As our measurements of the universe have become more precise, the data has become more fractured. Instead of a unified picture, we are left with three distinct mathematical tensions that current models cannot reconcile. The first is the Hubble tension. The expansion rate measured by the Cepheid distance ladder sits at 73.04, while the inference from the cosmic microwave background suggests a much slower 67.36. The second is the low redshift sound horizon. Independent measurements of the acoustic scale return a value of approximately 138 megaparsecs, significantly shorter than the 147 megaparsecs predicted by standard recombination physics. The third is a persistent factor of 1.65. This is the amount by which parameter-free derivations of the cosmological constant, calculated from subatomic sigma terms, exceed the value we actually observe. These are usually treated as separate problems. But physicist Boris Krieger has introduced a framework where all three are symptoms of a single variable, a lag parameter in the cosmic web, denoted as epsilon. If a single variable can resolve these disparate sectors of physics, it suggests that the standard model of the universe isn't broken, our perspective of it is. Observational cosmology relies on the assumption that late-time standard rulers, such as galaxies hosting supernovae, perfectly track the smooth, co-moving expansion of the background space. Because of this assumption, discrepancies in the data are interpreted as a need for new physics. Models like early dark energy try to fix the Hubble tension by altering the physical expansion history of the early universe. Krieger's framework takes the opposite approach. It posits that the expansion history and the physical universe remain exactly standard Lambda-CDM. In this view, the discrepancy is methodological. The error lies entirely in how we calibrate our distance indicators against a background they don't fully participate in. To test this, we have to look at the three mutually exclusive channels through which a vacuum matter coupling can enter our cosmological models. The background channel modifies the dilution law of matter, which physically changes the expansion history and shifts the acoustic scale. The perturbation channel treats the coupling as a clustering fluid, which alters how fast cosmic structures grow and how they lens the background light. The calibration channel changes no physical equations. It only modifies the observer's inference by accounting for a systematic offset in the measurement tools themselves. Krieger tested the first two channels by patching the class Boltzmann code to admit a fluid with a specific equation of state and a sound speed of 0. This subjects the model to the rigorous constraints of the microwave background. Any modification to the dark sector must account for the observed power specter to remain viable. The results showed that placing the coupling in the perturbation sector causes structure to grow far too rapidly. This happens because the matter species dilutes faster than normal while providing no outward pressure to resist gravity. This drives the structure growth parameter, sigma 8, up to 0.93, which is far beyond the limits set by our observations. This class output shows exactly why that physical modification fails. While the model can be tuned to preserve the acoustic scale, the bottom panel reveals scale-dependent residuals in the temperature data that the standard model cannot accommodate. Most significantly, the lensing potential shows a 34% displacement. This error violently exceeds the shaded gray band, representing the sensitivity limits of the Planck satellite. These results effectively eliminate the perturbation channel. The Hubble tension cannot be resolved by modifying the physical growth of cosmic structure. This exclusion points us toward the calibration channel, which relies on an overlooked state of matter. Standard cosmology recognizes co-moving particles that expand with space and virialized clusters that don't expand at all. Krieger introduces a third regime, the cosmic web. This network is neither fully bound nor freely expanding. It is a permeable structure that expands more slowly than the background. Krieger describes the web as a permeable string bag. While space expands around it, the web intercepts a fraction of the matter, creating a physical drag that causes the structure to stretch less than the space it occupies. This geometric penalty is the lag parameter, epsilon. In this regime, expansion follows the law of 1 minus epsilon. The problem is that our distance rulers, the galaxies we use to measure supernovae and baryon acoustic oscillations, sit inside this lagging structure. Because the structure carrying the ruler is lagging, the ruler itself reads short. A short ruler makes distances look smaller than they are, which artificially inflates the expansion rate we calculate. For this theory to hold, the lag parameter must be consistent across entirely different types of measurements. Krieger identifies three independent ways to determine the value of epsilon. First, The gap between the Planck background and the SH0 distance ladder yields an epsilon of 0.0778. Second, measurements of the sound horizon using time delay lenses, sharing no distance ladder calibration, yield an epsilon of 0.0618. The most critical test, however, is the hadronic derivation. This links the large-scale lag of the Webb to subatomic physics. The Webb's drag is determined by how much matter it catches, and that catch strength is fixed by the nucleon sigma term, a measure of how matter couples to the vacuum. By combining the sigma term with the known mass fraction of the cosmic web, Krieger arrives at an epsilon of exactly 0.0815 without consulting cosmological data. A value derived from the mass of a nucleon lands within a fraction of a sigma of two massive cosmological anomalies. This alignment indicates that the same lag parameter governs the sound horizon and the distance ladder alike. This brings us back to the final anomaly, the 1.65 factor that has plagued derivations of the cosmological constant. Krieger applies the lag to this problem through the slippage relation, which describes how the Webb's drag displaces the inferred energy density of the vacuum. Using a volumetric exponent of n equals 6, derived from the internal scaling of the theory, the hadronic lag of 0.0815 predicts a residual factor of 1.665. The data selects this specific exponent over alternatives, confirming that the lag acts on the volume of the measurement without changing the strength of the underlying vacuum coupling. In this framework, the background expansion and the growth of structure are perfectly standard. The Hubble tension and the vacuum overestimates are not failures of physics, but artifacts of measuring a smooth background from within a lagging web.